let's get started. So first of all, any questions? Yeah, regarding homework, exam, and so on. So basically, our final exam will be on April 30th, and it'll still be a take-home exam. Okay. And the final exam will cover everything after sampling, right? So I'll double check from which lecture, but it will not be comprehensive. Yeah.
Since it's take home, do we still have those 2 days to complete it?
Yeah.
So
It'll be the same as the midterm.
Until May 2nd to complete it then?
April 30th. Yeah, I think so.
Okay.
Yeah, 30th then. Yeah. So it'll be the same as before. So basically, I'll start it around 9 a.m. and then you'll have time until 2 days after 9 a.m. I think it's May 2nd. Yeah. Yeah, so the midterm will be uploaded probably tonight. So I almost finished all the grading, and I'm just double checking. I think all of you did a pretty good job. So yeah, I think I make it too easy for the midterm. Yeah, so yeah, I see lots of perfect grades. So for the midterm, yeah. Okay, but on the hardness, the level of difficulty you may expect is about the same as the midterm, right? So, but it will be on different subject, right? So it'll depend. Okay, great. So yeah, let's review what we covered in the last lecture. So now, in the last lecture, we talked about the general ML decision rule for multiple basis function, right? And then we talk about we start talking about this the spectral efficiency, right? So this is a general receiver structure of our AWGM model, right? So basically, what we do is that we assume R is our received signal, right? So this is a noise. This is a signal plus a noise, and then we pass that through this kind of structure, right? So basically, we multiply R of t by all of our basis functions, right? And then we do an integral for each of them, and then we get a received vector of it, right? So each element of this vector is a vector space representation of R of t, right? And then we're going to make our decision based on this vector, right? So basically, the idea would be identical. So we know what happened? So basically, yeah, this is the formula for each element in the vector of R, right? So we have this kind of signaling, right? So we can see that so R of j is so each element here is a Gaussian distribution with this mean and this variance, right? And then our noise is a white Gaussian noise, right, with 0 mean and not over 2 for the variance, right? So for each individual of them, it is very clear. But what is not extremely clear is that so what are the dependence between them, right? So what are the dependence on each element, right? So what we want is that they are to be independent, right? So in this case, the joint distribution would be very easy to write, right? Just a product of each marginal distribution, right? And then we figure out that, okay, so if the basis function fi and fj, so they are orthogonal, then basically all the elements here would be statistically independent, okay? So we covered that 2 lectures ago. And from that, so because they are all independent in R, so we can write the joint distribution of R given SI cent as a product of each individual marginal distribution, right, like this. Okay, and then after some manipulation, so we can see that so this is nothing. Oh, I forgot to remove this guy, right? Here it's not. Yeah, we don't need this here. So basically, yeah, ignore this, right? So basically, what we got is basically this, right? So here, remember that. So here, I want to derive our ML rule, right? So basically, for ML, we assume that all the signal will be sent with an equal probability, right? So therefore, the rule is that we need to find a I here or SI here to maximize this likelihood function, right? So basically, equivalently, is to minimize the distance between R and SI, right? So from this idea, so basically what we can get is that we want to find an I such that so the distance would be minimized, right? Still be like a Euclidean distance rule for ML rule in our case, right? So yeah, that is the case. And then we'll give an example on the 4-pan pulse amplitude modulation, right? So this is the general formula for the PAM modulation, right? We have AI, so that's the magnitude, so that's representing information. So I have 4 levels here. And the G of T is a pulse shaping function, and then we have a carrier function here, right? So given this, and we can characterize the frequency domain signal, right? So basically the bandwidth of the signal is determined by the pulse shaping, right? So pulse shaping will give you the bandwidth of signal, so which is very important, right? And for simplicity, we assume that we use a very simple pulse shaping, so which is basically a square waveform, right, like this, right? So then, now the question is to find the base function here, right? So in our case, in this case, so we find there's only one dimension in the signaling, right? So basically we use just one base function, so that'll be enough. Okay, so basically what we do is that we just try whatever we have done before. So we normalize any signal here as our basis function. So, right, so now we pick S0. So if you pick S1, S2, S3, so they all work. Okay, and in order to characterize that, now the question is that we need to characterize what would be the norm of S0. Okay, so now for simplicity, we assume that from the A0, A1, A2, A3 would be equally spaced like this, 1 minus 1, 3 minus 3, right? And then we can compute the energy of SI, right, given by the norm square of it, right? And then, so we can compute the energy of each symbol is this value, right? And then we take the square root of it, and we can get S0 equal to that because A0 would be 1, right? And in this case, we can characterize our base function is given by this formula, right? Because we just have one base, we can call that F0 or just F of t. Okay, so this will be our base function, right? And given our base function, then we can characterize all the SIs and RIs and so on, right? So basically, if we compute the inner product between SI and FT, and then we can get SI, right, which is our signal space representation. Okay, and in addition, using this SI, basically we can write SI as a product of this SI and our base function. Okay, and in order to simplify our presentation and compare with the other kind of constellation, so basically we want to write all the S's, from S0 to S3 in terms of the average symbol energy. Okay, so basically what we can do is that, so we have our energy formula, right? So which is given by this guy, right? So we know our energy formula, so we just want to characterize the average of it, right? And when A is 1, then, so this would be the energy, right? And when A is 3, so this would be the energy, right? And then we just characterize the average of it. So here should be 4, not T, it's a typo. So 1 over 4 here. So then the average symbol energy is given by this, right? And then using this information, so we can write down the representation of all the S's in terms of the energy, right? So which is ES over 5, square root of ES over 5, and here is the 3 times square root of ES over 5. Just remember this value, so we'll probably use it there next time, next lecture. Okay, so this is our, so this is for PAN, right? And then after that, so we have everything, right? So remember, so this will give us the value in the constellation, okay? And given this, so we can characterize the distance between R and S, right? So which is given by this figure, right? So basically now our constellation is given by these 4 points, right? And we write that in terms of the average symbol energy, right? And we can see the distance between 2 adjacent symbols will be 2 times square root of S over 5. Okay, and from here, because our rule is a distance, Euclidean distance decision rule, right? So basically, we don't figure out, given R, so which S is the nearest one, right? For example, if R is in this regime, then S0 will be the nearest one, and so on, right? So then basically, we can characterize which S is sent, okay? And this is our general ML decision rule, okay? So that clear? Any questions? That make sense? All right, so and next we talk about our spectral efficiency. So basically, for our spectral efficiency, you want to characterize, so our goal is to achieve a high data rate using very little bandwidth, right? And then, yeah, because, so what our metric before is kind of like bits per second, right? But now we have another dimension, which is the bandwidth. So bit dimension is not enough, right? So I want to normalize the bit error, so the bit rate over the bandwidth, right? So this is basically called the spectral efficiency, right? In order to characterize it, and so we have some notation here. So we denote TS as a symbol duration, and RS is just the 1 over TS, which is called symbol rate. And here we have a concept called MRE modulation, right? So basically, capital M here is the cardinality of the number of signals in our signal space, right? So this is not the signal dimensions. Just be careful on that. So basically, we use small m to denote the number of bits we can transmit every symbol, right? So So we have so far we have seen the BPSK, right? So basically, we have two symbols S1, S2, S0, and S1 there, right? So which is the antipodal case. So in that case, we have 1 bit per symbol, and for 4 PAM, so we have 4 symbols here, right? And then basically we can transmit 2 bits per symbol because we have 4 cases, right? And now we can characterize the bit rate, right? The bit rate is just number of bits per symbol times the number of symbols per second, right? Then we can characterize the bit rate as m times rs bit per second, right? So we have kind of seen this before, right? So if you recall, I think that is where we stopped last time, right? All right, so yeah, let's continue talking about the spectral efficiency today. Today is our lecture number 27, and today we're going to talk about spectral efficiency. Right, and then we'll talk about the error probability. Okay, so basically from the error probability, we're going to introduce the concept of the energy efficiency, right? Okay, great. So yeah, let's continue. So basically, so the bit rate RB just equals to m times rs, which is symbol rate, bits per second, right? So m is basically log m base 2, right? So this is our m is our what? Modulation order. Right? So now let's introduce the bandwidth, right? So we let capital B to denote the signal bandwidth. Right, so this will depends on what kind of the pulse shaping and so on, right? So B is the signal bandwidth. Okay, so now let's define what is spectral efficiency. Okay, spectral efficiency normally is denoted by eta, so that is nothing but RB divided by the bandwidth. Okay, so now let's see the unit of it. So basically, the unit of bit rate is bits per second, right? And the unit of bandwidth, we let that to be hertz, right? So basically, the unit of eta is what? So the unit of eta is bits per second per hertz. Okay, so that's spectral efficiency. Okay, so for example, Yeah, let's say for Wi-Fi, for the like old Wi-Fi, IEEE 802.11 A over G, right? So this is the old version of Wi-Fi, maybe Wi-Fi 3 or Wi-Fi 4, right? In that case, eta is equals to, the bit rate in that case is 54 megabits per second, right? And the bandwidth for Wi-Fi is 20 megahertz, right, normally. And if we compute the spectral efficiency, is 2.7 bits per second per hertz, right? So this is a normal number that you'll see for spectral efficiency, right? So basically, every second and hertz, you can transmit 2.7 bits, okay? And then you can expect like 54 megabits per second if you have 20 megahertz of bandwidth, okay? All right, so yeah, the concept is very simple, right? Just normalize the bit rate by the bandwidth, right? So now let's fit that in the framework that we introduced before, right? We'll talk about sampling, okay? So, and the Nyquist rate, Nyquist sampling rate, and see how we can characterize the eta in a probably easier way, right? And the key is to characterize what kind of bandwidth we need to transmit a signal, okay? So let's recall what we have covered before. So basically, what we need to recall is from our lecture number 24, right? So that's where we talk about our sampling and how many bits we can transmit using the sampling scheme that we used before, okay? So in that case, so now let's decide what kind of what's the bandwidth, what's the minimum bandwidth we need to transmit certain signal, okay? And given the Nyquist sampling rate, okay? So let's see whether that makes sense or not. So basically, in this case, the minimum bandwidth to send our pieces of information right, by pieces of information, basically we mean the sampled information, right? The sampled. This is our sampled information. Okay, so now we pick our sampling rate. So sampling duration is Ts, so sampling rate is 1 over Ts. So that makes sense, right? Ts there is what? Yeah, so that is shown in the slides. So basically, it's a symbol duration, right? So basically, the symbol duration will be the same as our sampling duration, right? So we just use the Ts symbol. Yeah, before when we do the use Ts here, S means sampling, right? But here, S means symbol, but they will be the same, right? In our case. Okay, so at this sampling rate, so can you tell me what kind of bandwidth we need? So to make the signal passing through the channel. Okay, so now we need to determine the signal bandwidth. Oh, sorry, the channel bandwidth. Right? Can you tell me? Right, so basically, yeah, let's recall a little bit. Let's say here is our signal, right? Let's assume this is our signal bandwidth. Yeah, so I want to use B here. So basically, yeah, use B for our channel, right? So maybe I just use B prime. Yeah, right? So remember that after sampling, so what we got is something like this, right? And make the signal periodic, right? So here would be our sampling frequency, right? So now, so can you tell me what kind of bandwidth we need to make our signal passing through the channel? But remember, right, we'll consider a linear system when a signal passing through a channel in a frequency domain. It's just multiplication, right? So basically, let's assume like our channel look like this, right? To make sure that the signal passing through our channel, so we basically need to make sure that, so what's the value of this guy here? I mean, you cannot, just, yeah, what I mean is that, so what is the requirement for the width here, to make our signal passing through our channel, right? Yeah, when we think, the midpoint here is just 1 over Ts over 2, right? So this 1 over Ts over 2, can be as big as B prime, right? So the extreme case is that this point, they will overlap, right? Because by the Nyquist sampling rate, then we just need to make sure that sampling rate is bigger than the 2 times this guy, right? Therefore, to make sure so the channel is wide enough to passing our signal, we need to make sure, let's see whether it makes sense or not. We need to make sure that the B for our channel has to be at least 1 over 2 times TS. Does that make sense? Right? Otherwise, if they touch each other, then we cannot make the signal passing through the channel. Right? That makes sense? Yeah, because this is the midpoint here, right? We need to make sure the channel bandwidth has to be at least as big as this point. Okay, so if that is okay, so basically, let's see. So in general, in our case, especially in our class, we just consider the DSBSC, the DSB kind of signal, right? So this double sideband signal, right? For double side signal, so we consider the whole as the bandwidth, right? We need to make sure the bandwidth can cover both sides, right? Not single band side, right? So basically, let's say for double sideband, okay, or our DSB signal. So basically, in this case, the requirement is that the bandwidth has to be bigger than, we need to make it larger, right? 1 over TS, right? Because now the whole is the bandwidth, right, for DSB. Okay, so that will be our requirement. Okay, great. And this is basically the requirement for the bandwidth, right? So, but what is the common estimate for the bandwidth, right? So would this be good enough, or this could be good enough, right? For DSBSC, so this will be the minimum, right? We need to consider, right? Does it make sense that we just assume B equal to this guy? Sometimes yes, sometimes no, right? So when it is roughly, we can estimate the channel bandwidth as this guy is when the modulation is linear and memoryless. Okay, so let's see so what is the linear and memoryless? So basically, yeah, we consider a linear and memoryless modulation. Okay. Okay, so basically, linear means follows. So SI will equals to AIC GT cosine 2 pi FCT plus AIS GT psi 2 pi FCT, right? So if this is this form of modulation, then it's called linear, right? Therefore, you can imagine the general frequency modulation will now belong to linear modulation, okay? And for memoryless, so memoryless is a requirement on this GT here, right? So basically, for when t is less than 0, so GT has to be 0, right? So let's write it down. So for memoryless, we require GT equal to 0 when t is less than 0, or t bigger than TS, right? So this is called memoryless. All right, so for example, our BPSK, our 4-pan, so they are all linear and memoryless signal, right? But for example, for BFSK, so that is not, so this is not linear and memoryless, right? So this is not linear, okay? Great. Yeah, and okay, the reason we talk about that is that for the linear and the memoryless modulation, so basically we can assume, right, for this kind of modulation, we can estimate the B as basically 1 over TS, right? So we can assume the bandwidth is that, right? In practice, it will be not exactly like that, right? Roughly speaking, it will be like that. So, but for FSK, you may think, right? So normally the bandwidth is not exactly that, but we need to consider the modulation index, right? The frequency index. Yeah, remember that? Yeah, we need to use this formula. Use this formula now. RB over B. Okay, in this case, for the linear and memoryless modulation, so linear and memoryless modulation. Okay, so in this case, so we can see what R eta equals to. Okay, so let's see how many bits per symbol. So we assume that is m bits per symbol, right? And then how many symbols per second? How many symbols per second? You consider, our sampling case, right? So TS is our sample duration, right? So 1 hour TS would be our sampling rate, right? So this is the bit rate multiplied the sampling rate, right? So this is bits per second. So this is this is a bit per symbol, and this is symbol per second, right? And then we need to normalize it by the bandwidth B, right? What's the bandwidth, roughly? 1 over TS, right? Okay, and then we can see this 1 over TS and this 1 over TS canceled. We just have m bits per second per hertz, right? Which is very nice, very simple, right? Remember, what is m? Log 2 of n, or this is modulation order. Okay, for example, let's say if it's for BPSK, right? For the linear memoryless modulation, so can you tell me what is the eta? Yeah, what is eta for BPSK? 1, right? Very good. 1 bit per second per hertz. And how about for PAM? 2, right? Very good. Okay, very nice. So yeah, this is okay. Then we can just determine eta using this, right? So basically, in practice, we can also infer the bit rate using eta, right? So this is nothing but eta multiply what? The bandwidth, right? So that would be our bit rate, right? So now let's take a look at okay. Okay, so now let's take a look at the Wi-Fi case. See an example. So yeah, as we said, right? So normally the bandwidth for Wi-Fi is 20 megahertz, right? So this is before, right? So 20 megahertz is a unit bandwidth for Wi-Fi. So now we can have up to 160 megahertz, I think. Okay, so now let's see. Let's say if BPSK is used, right? So for if I tell you it's for BPSK, we always assume that we have a linear, memoryless modulation, right? So if BPSK is used, then you know eta is what? 1, right? Okay, and then you know bandwidth is 20 megahertz, then you can compute the bit rate, right? It's the eta multiplied b is the 20 megabit per second. Okay, so this is how we use it. And let's say if 4 PSK, for 4 PAM is used, right? Similarly, 4 PAM will tell you eta is 2, right? 2 bits per second per hertz. And then RB would be given by eta multiplied b is 2 times 20 megahertz, right? That would be 40 megabit per second. Okay, you can see if 4 PAM is used, then our bit rate doubled, right? Which is pretty nice. Okay, then now the question is that in practice, why do we want to use BPSK? Right, so this is much better than that, right? So why do we even bother to use BPSK? So we do use that in practice. Okay, we use both of them. Yeah, for PAM, I'm not sure. Yeah, whatever. We'll use both of them. Right, so what's the motivation? From the spectral efficiency point of view, 4 PAM is much better, right? So if we still use BPSK in practice, there will be some other reasons to use it, right? So why we want to use it? Yeah.
Maybe 4PAM has a higher error probability.
Exactly, right? So 4 PAM will, so it's very good in terms of spectral efficiency, but it will not be extremely good for the error probability. Okay, so there's a trade-off. So now, yeah, let's talk about the error probability. Okay, so for error probability, as we said before, so we're going to introduce another very important concept, which is called energy efficiency. Or signal-to-noise ratio, right? So so error probability is a function of it. Okay, so now let's introduce some notation here. So basically, we assume PS. So that's the error probability. So which is the probability of a symbol error. Right, so this is pretty important, right? So in this class, we just focus on the symbol error. So what is the chance that a symbol is wrong? Okay, so don't talk about bit error, right? Symbol error, right? So bit error and symbol error are two different animals. So yeah, symbol error is much easier. So then we called PS, comma I. So this is the error probability that given SI is sent. Okay, so this is error probability. Okay, so now let's determine what does this equals to, right? So basically it means that SI is sent, right? But we don't think SI is sent, right? So basically I hat is not I, right? So basically this is all the case of Sj hat, but J and I are not equal, right? We assume this is the estimated symbol using our ML rule. Okay, right? So union means or, right? Either Sj or another Sj, but J cannot be equal to I. So that will give us the error probability. Does that make sense? Okay, so we're going to come back to this formula probably next lecture. Yeah, this is a kind of important formula, and this is hard to characterize because of this union. Okay, So what is easy to characterize is when the number of symbols is 2, okay? Or our antipodal case or the orthogonal case with just S0 and S1, right? So that's when it is easy to think about, right? So then we're gonna start with the binary case. The binary signals. All right, so for the binary signals, we have only 2 cases. So one case is PS, 0. Remember the meaning of the notation. So this basically means that we determine that we receive S1 given S0 is sent. Okay, and the PS, 1 is that we think S0 is sent, but actually S1 is sent. Okay, so those are the error probability. Okay, so just notation, right? So now let's compute it, right? So for example, as this guy, so what does that equals to, right? Because we're using our ML rule, right? Let's assume that this ML decision rule is used. Okay, so remember ML rule is a distance rule, right? So yeah, maybe I'll remind you a little bit. Yeah, let's draw this. Yeah, so basically, yeah, for this case, so this is our probability distribution, right? Let's assume this guy. So we always let here is S0, and here, or vice versa. Yeah, normally assume this is S0, this is S1, right? So yeah, and let's see. So this is basically FR given S0 is sent, and this is nothing but FR given S1 is sent, right? And remember, so basically, so this is our decision region, right? So this is intersection, and this is our gamma. ML is our decision threshold, right? Normally equal to S0 plus S1 over 2, right? And if for the ML, okay, and our decision region is that, so if on this side, so we're this is we're gonna determine that is this side S0. Right, and on the other hand, on this side, it will decide S1, right? So this is basically the case, right? And so the ML rule tells us it's a distance-based rule, right? So basically, let's say, okay, if R is here, let's say if R is here, right, then we're going to compare the distance between R and S0 and R and S1, right? Clearly in this case, the distance between, so this distance is smaller than from R to S1, then we're going to determine that is S0, okay? So that's the ML rule. But when we made a mistake is that, okay, so now, when we made a mistake is that, so when R is received, so when S0 is sent, so R will not be here. So R will be here, right? That is where we made a mistake. Is that possible? Yes, of course, right? Because we have some non-zero probability, right? So remember, the probability will go on forever, right? So the probability of this guy will also go on forever, right? So what is the probability that S0 is sent, and but R is here? It's basically the area falling down here, right? That's the probability that we're going to make a mistake, right? So then basically that's the error. How do we compute the error probability? Right? So let's summarize a little bit. So basically, what we do here is that, so this probability is nothing but, so our distance, the distance between R and S0 is bigger than, Where's the eraser? Right, the distance between r and 0 is bigger than the distance. Yeah. Between r and s1, right? Then we're gonna determine. Yeah, this is again so given as 0 is sent, right? So when the distance between this and the distance of this is bigger than that, then we're gonna make a mistake, right? That make sense? Okay, or the distance between r and s1 is less than the distance between r and s0. Okay, so basically, yeah. Now let's try to characterize the probability here, right? Let me think. Yeah, I mean this marker is dying, so I'll use this blue one, which might be better. Okay, so let's make it more more explicit when we characterize this probability. Okay, so do you remember what is the value here? Yeah. Very good, right? This is the square root of e, and this is the square root of minus e, right? And then we can see, the distance between these two. Yeah, I'll just write that. So the distance between these two is what? 2 times the square root of e. Okay, very nice. And given this, so let's try to characterize the probability there. Okay, so. So can you tell me, what is the how can I ask this question? So basically, it's a Gaussian distribution, right? So we introduced the Q function before, right? Do you remember what's the Q function? Yeah.
Like the survival function?
Yes. The standard normal distribution for, let's say, let me try to remember. So basically, let's say Q alpha is a probability that basically x bigger than alpha for standard normal distribution, right? And in our case, so basically, I mean, if alpha is equal to ml, so this will be this area, right? Let's consider standard normal distribution, but this area and this area will be symmetric, right? So basically, we can use the Q function to characterize this area as well, right? So basically, because the Q function is for standard normal distribution, right? So this is for a Gaussian 0, 1, right? Mean 0 and the area and the variance 1. So basically, in order to characterize this area, so this doesn't matter, right? So we can shift it to 0, right? What matters here is we need to make sure that the variance is 1, right? So basically, how can we do that? Right, the variance of this distribution is something we know, right? So the variance of this distribution is what? It's n naught over 2, right? So this is what we characterized. And then by doing that, so we can write this as a Q function, right? So basically what we need to do is that we need to normalize it with the standard deviation of noise. Right, in our case, it will be n naught over 2, but on the top, on the upstairs, we just need to characterize what is this alpha, right? So then, we need to shift this, for example, to like here, and then this value would be our alpha, right? And what is this value? It's nothing but d over 2, right? This is the distance. And the length, I mean, this value is nothing but d over 2, right? Or, we need to characterize this value, right? That makes sense, right? So basically, upstairs, we have nothing but d over 2. Right? So this, which is basically this distance, right? So the distance here. So it's the distance from this point. Let's see, from the mean to the threshold. Right? Okay, and then this is basically the error probability, right? Hopefully it makes sense to you. Okay. All right, and given this, so we know the standard deviation of the noise is n0 over 2, and then we can compute this as d over 2 divided by n0 over 2. N0 over 2 is the variance, right? So we need to take a square root of it. Okay, and then we know that d is what? 2 times square root of e, right? Then we can write that as square root of e divided by square root of n0 over 2, right? And then it will be equal to q of square root of 2e over n0. Okay, so this would be the error probability given S0 is sent. Okay, and let me imagine, right, the probability that will make an error when S1 is sent will be the same. Okay. Okay, so a few remarks here. So now we can see there's a very important term here, which is E over N0. Right? Remember, what's E? The symbol energy. Right? The energy of S0 or S1, and N0 is noise variance. Right? Technically, you know, it's a variance of the projected noise on our base, right? So technically, you know, N0 over 2 is a variance, but we consider that's kind of the variance, right? Because it's kind of neat. We don't have any constant here. So basically, we call that the signal to noise ratio, or SNR. Okay, in our case. And the important thing is here is that what kind of signaling that we use, for example, like BPSK, or you know, we use orthogonal signaling, right? Like what is that called? Is the orthogonal signaling? Is there a name for it? I forgot. Anyway, so we have seen that before, right? And for PAN, whatever, right? For all the signaling that we use, and when we characterize the error probability, so this term would be appear everywhere, right? Always appear, right? The difference is this guy, right? The constant in front of it will be different for different constellation or different signaling, right? Okay, so that is that's it. Okay, so yeah, now let's try give an example to see. We have 1 minute, so that should be sufficient for a simple example. Yeah, let's see a simple example here. Yeah, let's assume that the probability of error is 10 to the power 5, right? So this is normally the order we're considering in practice, right? 10 to the power of minus 5, or you know, even less than that, right? Okay. And now let's assume that we use BPSK, right? And let's characterize what is the required signal-to-noise ratio to achieve it, right? So it's kind of straightforward. So we know the error probability Q, is equal to Q square root of 2e over n0, right? And this is nothing but 10 to the power of minus 5. So by the way, so this or what we write here, so that is just the error probability of the BPSK, right? Because this is when S0 is sent, when S1 is sent, it will be the same, and then we'll average them. That will be the total error probability, right? So this will be just the error probability for BPSK. Okay, and then so we can characterize square root of 2e over n naught. That will be equal to q 10 minus 5 inverse, right? So we're going to see how we can get this number in the next class. So this can be obtained by using the tables or use Python. Okay, so yeah, because this function we can now compute that by hand. Okay, and then we can see 2e over n naught is nothing but, so this guy is squared, right? And the e over n naught, we can just move this half on this side, right? Would be given by this number, okay? And we just compute that numerically. We can get our desired signal-to-noise ratio. Okay, so that's how we compute it. So we're going to have something like this in our final exam. Okay, I think we have one small question like that in our homework, but we're going to have something like that in our exam. All right, and so we're almost done. So in the next lecture, so we're going to see the general case. See one more example on this, and then we're going to see the general case, like when we have multiple bases, and then non-binary case, then how we can characterize the error probability. In that case, we really need to evaluate this, which is not easy to compute, and then we're going to approximate this, right? So which is also pretty straightforward using our method. Okay, and then we're done, right? Okay, yeah, thank you.